My name's Oliver. I'm from UniMelb and working under the Ausgrav Centre of Excellence. So today, I want to talk about collisional N-body simulations, black hole binaries, and my love-hate relationship with FORTRAN. So that's quite a big, clunky title, I'm aware. So just briefly before we get started properly, I'll break down some of these terms. So collisional N-body simulations, they just refer to simulations of gravitating systems of particles, normally quite dense ones, where we integrate the equations of motion directly. Black hole binary mergers, pretty simple. It's, as the name suggests, you take two black holes, they're in a binary, they in-spiral and merge, and then you get one bigger black hole. FORTRAN, for those of you that don't know, is a very old coding language. Some would consider it obsolete, but my talk should be evidence that it's not. And it was actually the first properly used interpreted coding language. It was developed in the 50s on punch cards. And I had to learn it for a lot of my research. And for those of you physicists in the room, love and hate are human emotions. You may have heard of them. So, a bit of an overview of this talk. We're going to start by discussing in a bit more detail N-body simulations. You know, what are they, and what do people like me use them for in terms of research. Then talk a bit about black hole binaries. How do they form? How do we detect them? Why do we care? And then I'll discuss some of the updates and upgrades I've done to my N-body code and discuss some of the specific changes I've made and some brief results. And those all required just way too much FORTRAN. If you like FORTRAN, that's fine. I don't mind it anymore, but I guess I'm probably indoctrinated. So first of all, collisional N-body simulations. So an N-body simulation, as I said, it's a system of N particles. N can be whatever you want. And the system evolves due to the mutual gravitational effects of every body on every other body. So take, for example, we have this orange body here. It feels some gravitational force from this green body and this blue body. And in an N-body simulation, in this case n equals 3, what we do then is we sum the gravitational force of those, the green and the blue particle. Then what we do is we use that gravitational force to calculate a momentary velocity and acceleration, and we pick some discrete time step delta t. It can be whatever you want, but in general, smaller time step would mean more accuracy, larger time step, less accuracy. However, larger time steps means you don't need to do as many time steps to simulate the system, so it's quicker. So there's kind of a trade-off between accuracy and speed. But then we can use this to calculate the equations of motion, and then you just do that over and over again for however many time steps you want, and they just evolve away based on their mutual gravitational force on each other. Now, this is a pretty simple system of 3 bodies, and it's in 2D. It gets a bit more complicated, as I'll discuss. But as I said, like in the title, this is for collisional N-body simulations. So you might be thinking, well, what does collisional mean? So in general, there are 2 main kind of umbrella types of gravitational systems of particles, collisional and collisionless. So collisional these systems, they're very dense, so like high stellar densities, so the stars and black holes and everything are very close together. And that means that there's a lot of close interactions between each particle. That leads to a lot of a rapid exchange of energy compared to the dynamical timescale of the system. So with all these 2-body interactions, they like the specific interactions between like 2 stars tend to dominate the dynamics. Also, I'll just say that if I say particle, what I mean is either star or black hole or whatever we're talking about in the N-body simulation. It's just kind of a generic term that people doing these simulations refer to for any sort of thing in the system. So a good example of a collisional system is a globular cluster. And those are what I predominantly care about and simulate. Collisionless systems, on the other hand, are diffuse. So compared to a collisional system like a globular cluster, the bodies tend to be fairly far away from each other. This means that they don't really interact much directly with each other, so you don't get really two-body scattering or anything like that, which, as a result, there's a very slow evolution in the system, slow exchange of energy. So essentially, the dynamics of the system is dominated by the mean field, like the cumulative sum of gravitational forces from everything, instead of these like rapid two-body interactions that happen on quite a short time scale and can change quite quickly. It's this more cumulative sum effect. And a good example of a collisionless system is a galactic cluster. Because the galaxies aren't close enough to directly interact, you can simulate it as a collisionless system. For the rest of this talk, I'm going to focus on collisional systems just because that's what I care about and simulate. I don't have anything wrong with collisionless systems, but it's just not my area of expertise. So as I said, I mainly care about globular clusters specifically. So for those of you who don't know, globular clusters are dense spherical collections of stars that tend to orbit in galactic halos. So for example, the Milky Way has of order 150. And these are pretty cool because they're quite old. So the stars can be like around 12 gig years old. They have quite low metallicities due to that age. And they display what we call mass segregation. So basically, there's a big density contrast between the outer regions of the cluster and the dense central core. So the core will have much more heavier mass stars and black holes, and then the outer regions will have more lighter mass stars. And the core tends to be very, very dense. This can be up to about 100 stars per cubic parsec, which is kind of important. I mean, that's where it comes into being a collisional system, because it's got these very high stellar densities. You get a lot of close interactions. And as a result of these low metallicities, the large amounts of mass segregation, and the very dense core, they are very good, essentially, gravitational wave factories, if you will, because you end up with more or less a dense core of black holes, because once the heavy stars go supernova, black holes become the most massive bodies in the system. They migrate to the core, and then with those high central densities, you can get a lot of interactions. So the way that I and a lot of other people simulate globular clusters to learn more about them is through an N-body code called NBODY 6. And you see here on the right just a 2D slice showing, I think it's 100,000 particles using N-body 6. And N-body 6 is a state-of-the-art N-body integrator. It's been built over decades. The first version, N-body 1, was developed in the 1960s by Sver Arsev. And Sver is essentially the godfather of N-body simulations. He's essentially dedicated his life to developing the series of code, with the newest one being N-body 6. And over the years since the initial version, him and a whole bunch of collaborators such as Rosemary Mardling and Seppo Mercola have helped to implement both new physics into N-body 6, as well as better numerical methods to help do the force calculations more efficiently. N-body 6 contains stellar evolution packages through SSE and BSE, which was developed by Jared Hurley, who's now over at Swinburne. And it also has a special treatment of close systems such as binaries and triples, which is important for when, like me, you care about things like black hole binaries. I'll just point out that, because people often ask me about N-body 6, have you thought about converting it into C++ from FORTRAN? N-body 6 is a very big code. It contains like 350 scripts of FORTRAN. Some of those are thousands of lines long. And there's also, some of that is also in CUDA, because it's got GPU implementation for certain things as well. So basically, yes, I have thought about it, but I don't really have the time or expertise to do it. It also means that getting started with N-body 6 can be a bit daunting. But if anybody in the room wants to, you have me, so feel free to reach out. But since it's such a big code, it's probably important for me to briefly describe just some basic concepts, some numerical methods that it uses. So there's kind of 4 key ones that I want to highlight. The first, and probably most important for any N-body simulation, is how does it deal with the forces? How does it integrate the equations of motion? In this case, N-body 6 uses a 4th order Hermite integration scheme. And this allows for efficient and accurate force calculations. And then, in addition to that, it implements a neighbor scheme, which basically splits up the force on any given particle into both a regular and irregular component. So the regular force component is the force felt due to the distant particles. So because particles far away from a given body have slowly changing forces, so they don't need to be calculated too regularly. And in N-body 6, with GPU implementation, GPUs are used to calculate those regular forces. And then you have the irregular forces, which is the close range forces from particles close to whatever body we're talking about, that tend to vary on a much shorter time scale, which means they need to be calculated more frequently in order to achieve some given numerical accuracy. So the neighbor scheme is a way of doing this whereby for every particle, take for example this big purple one here, you define a neighborhood radius, denoted here by this pink dotted line. That neighborhood radius is specific to each particle, and it's calculated based on the density, the contrast where that particle is located. And any objects or particles inside that neighbor radius, so in this case these lighter particles here, those will contribute to the irregular force and be calculated more frequently, and they're called neighbors of the object. And then you have the ones that aren't the neighbors, these outer ones, the darker ones, outside the neighborhood, that contribute to the regular force, and they're calculated less frequently. And this essentially just means that the force, not all forces have to be calculated so frequently, which basically just speeds up computation. N-body 6 also implements individual time steps. So each body will have its own time step associated with it. We don't have any global time steps. And this is good because if you have one system, like a binary or some complicated hierarchical system in the core, where it's very dense, they'll need quite a small time step to achieve some accuracy. But then in the outer reaches of the cluster, where it's a bit more diffuse, you don't need nearly as low a smaller time step in order to achieve that same accuracy. So it's nice to be able to pick different time steps depending on, for example, the density at any given point in the cluster. And the last thing is called regularization, KS regularization. And this is what I flagged earlier, the special treatment of closed systems such as binaries. And basically what it does is you replace the binary with a kind of center of mass ghost particle for the force calculations in the N-body simulation. And then you calculate the internal motion of the binary analytically using some coordinate transformations. The details are a bit complicated, and I won't go into them now. But essentially what this means is you don't need a prohibitively small time step to calculate the internal motion of the binary, because you can just do it analytically. And in the newest versions of N-body 6, they have algorithmic regularization. So it's not limited to just binaries. You can do like triples and quadruples and order 5, so you can do this for higher order systems, not just binaries, and it's essentially a way to speed up computation. So you might be thinking, well, that's great, Oliver, but how well does it run? I mean, if you may be interested in numerical methods and benchmarking, well, so I've done some tests for a project. So firstly, this is looking at how fast it runs for 32 mega years of cluster evolution using multiple different initial particle numbers. So the blue dots represent the actual run times in minutes for this 32 mega years for the different particle numbers, ranging between 50 and 200,000 particles. And as expected, you can see increasing the initial particle number means that the simulations run slower. It's not surprising. What is surprising is, so we do a line of best fit, and we find the trend is runtime in minutes scales as particle number to the power of 2.65. So for those of you that don't know, I don't know if you think this is good or bad, but to me, this is really good because the theory predicts that it'll be about n to the 3. So if we're doing better than theory, I'm happy. It still does mean, though, that if I want to run 200,000 particles, it's going to take about a month, assuming everything goes smoothly, compared to a bit less than a week for 100,000 particles. But you might think, well, one way we could speed it up is chuck some more hardware at it. That's obviously a good idea. So we can add more CPUs, and this is for 200,000 particles. Adding more CPUs works to an extent, but you tend to get diminishing returns if you go you can't just keep adding more and more and expect it to keep getting better. So again, we find doing a line of best fit, we find the runtime scales as number of CPUs to the power of negative 0.35. So I mean, this is just for 200,000 particles. It'll be different for 100,000 particles and also changing other things like the half mass radius and things like that. But this is essentially a good way to show that, yes, increasing CPUs can help, but only to an extent. So for this, I wouldn't go more than 10 or 12 CPUs, or else you're just kind of wasting resources. Also, the more CPUs you ask for, the longer it's going to take you to get those resources if you're using a supercomputer and waiting in the queue. But we also have GPUs. As I said earlier, thanks to Kaigo Nitadori, the regular force calculations are done on GPUs. So we can test, using OzStar, I only have access to either 1 or 2 GPUs per node. But as you see, it doesn't matter because adding a second GPU doesn't actually help in this case. So we have the same runtime scaling with particle number as earlier, but then with the dot dash green line, that's the same, essentially the line of best fit, like the dotted red line, except now adding 2 GPUs. And you see that it's consistently lower than the dotted red line. It's a bit bad. Adding more hardware should increase your speed, but in this case it didn't. And
this is runtime, so the GPU is below, so it's less runtime, so it seems to be better.
Sorry, I've mixed up the labels. Sorry, my bad. The GPUs are worse. Yeah, sorry. The green line is 1 GPU, and the red is 2 GPUs. My mistake. So yeah, it is worse. And some of the reason is because the code is not optimized. The CUDA code for GPUs is not optimized to run on either modern GPU hardware or also for multiple GPUs. So I do have a project with Kaigo to help essentially upgrade the CUDA code to be better optimized for more modern GPU architecture and also to be better scalable for multiple GPUs. You see that the scaling for GPUs is n goes as particle number to the power of 1.85. That is actually better than the 1 GPU case, but it seems based on this trend that that'll only matter once we get up to maybe 300,000 or 400,000 particles. So this is something that I need to look into a bit further, essentially run larger numbers and also do the upgrades. So that's a bit enough about numerical methods. Now we can talk a bit more about physics, so looking at black hole mergers and gravitational waves. So as I'm sure most of you are aware, back in 2015, we detected the first gravitational wave signatures. This is from a black hole binary merger, denoted as GW 150914. In the graph there, you can see the frequency versus time in the 2 detectors. So the LIGO is essentially a giant L-shaped laser interferometer, and there's 2 of them, one in Hanford and one in Livingston over in the US. And now, after 2015, there's been 3 observing runs, 01, 2, and 3. We have of order 90 black hole binaries, depending on how you count and which ones you include. But it's about 90. You can see there is, in blue there are all the black hole binary mergers. So there's a decent proportion across mass ranges. One of the biggest open questions for people like me in this field is, now we've got this big population of merging black hole binaries. So we want to see, how do they actually form? We want to know what, because all LIGO can tell us is, okay, there's been a merger. This was approximately the masses and spins of the black holes before merger, and something about the distance. But we don't know anything about it prior to that. We don't know how those black holes ended up together. We don't know in what environment they formed in. So this is an open question. How did these black hole binaries form? We know these black hole binaries exist and merge now, but we're not 100% sure how they form. There are kind of two main formation channels that people tend to talk about and lump them into. The first one is the isolated channel. So it's where you have a stellar binary that forms, say, in the galactic field. These two stars evolve together in the binary, but in isolation from any other star or body, so they only interact with each other in the binary. And then eventually, if things are right, you can undergo this thing called a common envelope phase. Now, I'm not an expert in this. There are some people in the room that know more about this than me, so I'm not going to go into any details so I don't embarrass myself. But at a very basic level, you can get unstable mass transfer from one star onto its companion. And when this happens, the outer region of the star that's doing the transferring of mass tends to puff up. This is called the envelope of the star. And then that's very important because as it puffs up, if the companion then is orbiting through that, there's a lot of drag. That drag leads to decay of the orbit, so that by the time the two stars go supernova and hopefully form a black hole, the orbit has shrunk enough so that then they'll be able to merge within the age of the universe. Because in order for them to be able to merge within the age of the universe, they need to emit sufficient amount of gravitational waves to decay the orbit further until they eventually in-spiral. And that obviously takes time and is dependent on multiple things, including that initial separation. On the flip side, we have the dynamical channel, which is where you have stars that form in a dense stellar environment, such as a globular cluster, and then they go supernova, form black holes. Then these black holes sink to the core due to mass segregation. They undergo a whole bunch of interactions, like 2 and 3 body scattering, and then eventually form a black hole binary. Then that black hole binary goes on to evolve via similar 2 and 3 body 3 body hardening and things like that. And as a result, the orbit can shrink significantly and also quite a lot quicker than it would through purely just gravitational wave emissions. And then so these are the two main different formation channels, and they do have notable signatures that you can use to hopefully determine between them. I'm not going to go into that today, but for those of you that know Shanika, she has done a lot of stuff about the black hole spins and the spin distributions, because it's quite different between isolated and the dynamical channel. So as you probably guessed, I'm only going to really talk about the dynamical channel because, as I've already said, I'm doing globular cluster simulations. Those are collisional, very interacting binaries and single bodies. So it's pretty much only dynamical channel for me, at least for this talk. And just a brief refresher on binaries before I go any further to make it a bit clear for some people that don't know or have maybe forgotten. For a black hole binary, there's a few key parameters. We've got M1 and M2, the primary mass and the secondary mass, where primary just means it's heavier. You've got some orbital angular momentum, J. Both of those two black holes have a dimensionless spin, alpha, which can vary between 0 and 1. And there's some separation, where in this case, we denote it as A for the semi-major axis. There's also eccentricity, but I'm not going to really talk about that today because that complicates things massively. And then you also have the mass ratio, which in this case I've done the symmetric mass ratio, denoted as eta. There's also just the regular mass ratio, which is M2 over M1. The only reason I give eta is because it crops up an equation later. And so we have this binary now. In the final phase of its evolution, when the orbits, they're orbiting very close to each other, the gravitational wave emission will be quite high, so they're in-spiraling, the orbit is decaying, and then eventually they'll merge together and form a new second-generation black hole. But this post-merger remnant has specific properties that we can calculate based on numerical relativity. So first of all, the gravitational waves carry away some of the mass from the binary. So this final black hole weighs a bit, it has a little bit less mass than the sum of the initial binaries. So there's a bit of mass loss. Also, due to conservation of angular momentum, because you've got the binaries orbiting, you've got the orbital angular momentum J as well as the spins. The final black hole has some post-merger spin. Gravitational waves do carry away some of that spin, but not all of it. And then, which is a particular thorn in my side, we have, if the gravitational waves are emitted asymmetrically, there's some linear momentum flux, because if you kick more gravitational waves out that way, then your black hole has to move that way. So you have some gravitational recoil. And here are the equations. Now, I know the rule is don't put too many equations in a talk, but I'm going to break that rule for the purposes of demonstration that I had to go through all these lovely looking equations and implement them into NBODY 6 in FORTRAN. So that was, as you can imagine, easy and very enjoyable. Basically, you all feel my pain. But yeah, anyway, look, yeah, okay, those equations are ugly. They'll hurt your eyes. So instead, I'll show you some nice graphs to make a bit more sense of this. So just looking at how merger recoil and mass loss changes by varying the mass ratio, you can see in red there's the percentage mass loss, and then in blue is the merger recoil. So you see merger recoil can be significantly high, but it's also not monotonic. I will also mention that the variation in these is due to randomly orienting the spins, because the spins have both a magnitude and direction. They're vectors, but for dynamically formed binaries, the spins are expected to essentially have an isotropic distribution. So we just randomly draw the spin orientations for the purposes of this. And important for me, I'm only doing globular cluster simulations. That's approximately the cutoff for the maximum central escape velocity of globular clusters. As you can see, most of these blue dots are above that purple line, which essentially means most of the merger remnants here, the second generation black holes, are getting ejected from the globular clusters after they merge, which is a bit annoying because if you can retain those, then you have a very heavy black hole that you can go and merge again, and you can use that to explain some of the things that LIGO have observed. And then varying the spin magnitude, again, percentage mass loss in red, recoil in blue, you see that increasing the spin magnitude tends to give you a much larger spread in possible recoils and mass losses. And this is kind of good because it means a higher spin means that you essentially have more chances to get a very high recoil than a lower spin. So if you have quite low spins, it's easier to get a low recoil and retain your black hole, essentially. So that's some details about how these post-merger properties work. Now I'll talk about, so as I said, I've implemented them into NBODY 6. So I'll just talk about that and give you some brief results. So basically, here's the recipe that I've got in my version of NBODY 6. First, when a black hole is born, I assign it some natal spin, if you will. And this is based off fitting formula that was derived through MESA simulations. And then I don't evolve that spin, at least in the current version, because although accretion does have the capacity to spin up a black hole, it's actually very slow. And these black holes, since they're in a very dense dynamical environment, they don't last long in with a stellar companion. So the effects of accretion are essentially minimal here, so I don't include it. So once I assign that spin magnitude at birth, it stays like that until a potential merger. Then when NBODY 6 says, yep, flag, we've got a merger, a black hole binary merger, I randomly assign those spins a direction. As I said earlier, since these binaries are formed hierarchically, you expect the spin distribution to be, spin magnitude distribution to be isotropic. So I just simply draw from an isotropic distribution there. Then, using those lovely equations we saw earlier, I calculate the properties, post-merger properties, the recoil, mass loss, and spin. And then, if the new black holes, the second generation black hole, has a velocity that is above the escape velocity, it gets kicked out of the cluster. Boo, can't stay around, can't have more fun and merge again. But if I'm lucky and the properties are such that the recoil is below the escape velocity, then the black hole sticks around in the cluster and it has its new properties based on the mass loss and remnant spin calculations that I showed you earlier. And just showing you some results. So this is looking at the recoil velocity. This is just kind of an artificial example. So NBODY 6 by default doesn't have any of these merger, like recoil or mass loss or spin or anything like that. So this is just looking at, in one simulation, I found a merger of a black hole that had a chain of 7. So the black hole merged, then it merged again and merged again. It did that 7 times. It ended up with a mass of around 100 solar masses. But as I said, that's not really realistic because it didn't include proper merger mass loss and it didn't include recoil. So looking at the first merger with a mass ratio of about 0.85, in this very dark blue you can see although the recoils can be as high as just above 600 kilometers per second, there's still a decent proportion that's quite low, below 100 kilometers per second. But once you start to get to the successive higher mergers in the chain, like mergers 3, 4, and 5, you can see here in the orange, green, and yellow, the lowest possible recoil is above 100 kilometers per second. So basically, no matter what, that black hole would get ejected from the cluster because the escape velocity for this cluster was only like 25 kilometers per second. So doesn't matter what you do, doesn't matter which way the spins are oriented, that black hole's getting ejected. Obviously, so for this simulation, those black holes weren't ejected because we did this in post-processing, but this is just to illustrate the effect of post-merger recoil. So in my new simulations that I've started running with this included into the simulations, pretty much all second-generation black holes are getting ejected after merger, just due to the extremely high recoil velocities. And then looking at remnant mass, this is just a few post-merger remnant masses from some of my newer simulations. You can see that there's a decent distribution between about low 30s to low 60s in solar masses. So we're actually starting to get up into that upper black hole mass gap. This is due to things like pair instability and pulsational pair instability supernovae that predict you shouldn't be able to get at least first generation black holes that are produced through core collapse supernova above about 55, 60 solar masses. But if you have black holes, first generation black holes that merge, you can. And this is just showing that. But this result here is very dependent on the specific supernova scheme you're using and also your initial mass distribution for stars. So the default NBODY 6 has it cut off at 100 solar masses for your stars, which is what this is based on. I'm going to do some, this is because I wanted to compare to the base version of NBODY 6, but in my newer code, I've also gotten rid of that 100 solar mass cutoff. So you can essentially start with heavier mass stars, which will lead to heavier mass black holes. I've also done some work on stellar evolution in the code, updated the stellar evolution models to be a bit more modern based on newer physical prescriptions. So these updates kind of have three different categories. The first one is stellar winds. So, as stars just sit there and evolve, they're constantly shedding material through what's known as stellar winds. So I altered the stellar wind prescriptions based on Bilczynski 2010. This leads to, among other things, heavier black holes. I also updated the supernova physics and remnant mass formation to include the pulsational pair instability supernova and pair instability supernova. And this is based off the Fryer et al. 2012 models. among other things, this also leads to heavier black holes. You might be sensing a theme here. And then natal kicks. I says as discussed, but sorry, I changed the order of that. Natal kicks are coming next. I'll discuss that in a bit, so just ignore that for now. But just a spoiler for now, that leads to more black holes retained. So a very like zeroth order, these updates mean that I get more black holes and they're heavier, which is good because for people like me that like looking at black hole mergers, that means more fun, more excitement. So looking at the comparison of the black holes, this is just taken from one of the base version of NBODY 6 and one with my updated code. In red is the newer version, my updated code, and in blue is the old one. You can see that in red, not only do we get much more black holes retained, so 107 black holes retained after natal kicks compared to 77, they also tend to be much heavier, so upwards of 35 solar masses. So as I said, the kind of zeroth order is that we get more black holes and they're heavier. This means we tend to get more mergers, and those mergers tend to be heavier as well, which more aligns with what LIGO is detecting. And now, natal kicks. So, and I didn't discuss it beforehand, but basically, natal kicks are what happens when a star goes supernova and it forms either a neutron star or a black hole. I mean, well, it happens for white dwarfs as well, but we don't really care about white dwarfs for this talk. Sorry if anyone in the room really loves white dwarfs, it's just not my area of expertise. But yeah, so when the supernova happens, if not all the energy is directed isotropically or symmetrically, then it's the same as the gravitational recoil. If more matter or energy is directed that direction, then your, black hole or neutron star, whatever's forming from the supernova, is going to get kicked that way. These are called natal kicks. The word natal here just means because the black hole is being born or the neutron star is being born. And a lot of work has been done to determine what these natal kicks are, at least for neutron stars. This is relatively easy to do. I say relatively compared to black holes, which I'll get back to in a sec. Basically, you can use pulsar proper motion studies. So you can observe pulsars and determine their proper motion to see how fast are they moving. And that should roughly be what their natal kicks are. So in this lovely plot by Wilcox et al., shout out to Reinhold, you can see that it roughly follows a Maxwellian distribution. And this is essentially what most people run with for these sort of simulations, a Maxwellian distribution with a mean of 265 kilometers per second. So that's all well and good, but as you're probably aware by now, I like black holes more than neutron stars. So what about black hole kicks? Well, unlike pulsars, we can't really do proper motion studies of black holes, because you can only really view a black hole if it's in, say, low mass X-ray binary, or from the LIGO ones that are merging, or even, I suppose, Event Horizon Telescope for the supermassive black holes / looking at high redshift quasars. But none of those really tell us anything about the proper motion of these black holes. So the natal kick distribution for black holes is very poorly constrained. But we do have some ideas about what it might be. A very common model is the so-called fallback modulated natal kicks. Basically, what you do is you take the neutron star natal kick distribution, like what I showed you in the previous slide, and then you modulate that based on how much mass falls back onto the black hole after the supernova has finished. And this is a very simple model. It's nice and neat because all you need to do is take this neutron star kick, which you draw from the Maxwellian distribution, and then you calculate this proportion of fallback, where F sub FB is the proportion of mass falling back onto the black hole. And then, essentially, this leads to smaller kicks compared to the neutron stars, because, so F sub FB varies between 0 and 1. 0 means no fallback. 1 means all of the mass from the star that exploded fell back onto the black hole. But there are also other models that we can look at. These are just two examples that I've got here. There's, a collapse asymmetry-driven and neutrino-driven. I'm not going to go into details about them. They're not my models. These were taken from Banerjee et al. 2020. The important part to know is that so there's the basic fallback one from previous slide. There's the collapse asymmetry-driven and neutrino kick-driven. I implemented all three into NBODY 6 to see how do these different kick mechanisms alter the final black hole's distribution. So the main thing to look at is retention. So as I said, if the natal kicks are really high, those black holes are getting ejected after being born. If they're low, then they get retained. So looking at this, you can see that the neutrino-driven model means that pretty much every black hole is ejected after born. The standard fallback model leads to about 1/3 being ejected from natal kicks. And then the collapse model leads to about 1/10 to, well, 10 to 15% being ejected. So this is lovely, but you know, these aren't really able to help us determine which natal kick mechanism is actually, you know, occurring in real world supernovae. So you might think, is there a way which we could work out which kick scenario is correct or more correct? Maybe. Bear with me. This is still a work in progress, but so what you can do is you can define this so-called core black hole mass fraction. The name is pretty self-explanatory. It's just the ratio of mass in the core due to black holes compared to the total mass of the core. So MBH is the core mass due to black holes, and then big M is just total core mass. In this case, we're defining core radius to be the three-dimensional radius containing 5% of the cluster mass. And the thing with this is we can't measure this directly, but it's a proxy for how many black holes are in the system. What we can see, though, is that in the simulations, over time, the core black hole mass fraction tends to decrease as black holes are ejected through interactions. But we can use structural concentration index, which is something we can actually measure to help determine core black hole mass fraction. So structural concentration index is another ratio. It's a ratio of the 5% light radius to 50% light radius. The thing with this is, as I said, we can measure this in real clusters because it's a two-dimensional projected radii. You can do this with a telescope. And looking at the simulations, you can see that also it tends to decrease over time. So we can look at a correlation between the two. And it's not the best correlation in the world, I'll give you that. But if we do a least squares fitting method, we think we can determine the core black hole mass fraction to within a factor 2 at 68% confidence. Again, I said this is still a work in progress. And this is based on some older simulations using the base level of the base public version of NBODY 6. So we would like to redo this with the newer versions. But it is a pretty good indication that we might be able to use structural concentration index to determine core black hole mass fraction. And based on core black hole mass fraction, you can use that to estimate how many black holes are in the system. So you could, and as I showed before, the different natal kick mechanisms lead to different number of black holes being retained in the system. So using this, we could potentially help determine which natal kick mechanism is favored. Obviously, we haven't applied this to actual observations yet, because I'm not really an observational astronomer, at least not yet. But yeah, this could potentially help to determine between different natal kick mechanisms. So, in summary, we've detected a lot of black hole binaries using LIGO. I mean, that's kind of the impetus for my entire research project. This is essentially, I sat down with Andrew in 2018, and he's like, right, so here's some black hole binary mergers. At that point, we'd only seen 10, but now we have about 90. An 04 starts in hopefully a few months, so we're going to start seeing a lot more. Globular clusters are really good dynamical factories for these gravitational waves. As I showed, they're collisional systems, And because of that, we can get a lot of binaries quickly, and those binaries can merge quickly. So it could be a potential formation scenario for the black hole binaries we're seeing in LIGO. I've used NBODY 6 to help simulate these globular clusters, and among other things, to try and determine, properties about the dynamically formed black hole binaries. And I've also updated NBODY 6 to include some newer physics, and I'm, as an ongoing project, also working on upgrading NBODY 6 to help speed it up with newer GPUs. So thank you, that's all. And just a little PS that if anyone has any ideas to upgrade NBODY 6 further, I'm always willing to listen and looking for new things to do. Or if you actually want to use NBODY 6, and specifically my updates to NBODY 6, feel free to reach out. Always happy to collaborate. Bit busy, but more work's always good. Yeah, but thank you.
How does the structured index tell you about the black holes in that you have?
Right. So
how do you deduce one of the other? How can you tell it's not, say, population of neutron stars? It's also non-shining.
Because in these simulations, at least the way we did the natal kicks. So we did actually retain quite a bit of neutron stars. It's a good question. We need to follow up, because in these simulations, the natal kick prescriptions in NBODY 6 by default are quite basic. They're just essentially drawing them both from a Maxwellian and then artificially lowering them based on the escape velocity of the star cluster. The reason why it does this is to essentially emulate a fallback style natal kick. It's not perfect, but at least for black holes, it's good enough. It does mean that we will retain a lot more neutron stars. So what I would have liked to do is redo this analysis, but with my new version, where we have the fallback modulated kicks for black holes. And for neutron stars, I'm using the Muller-Mendel kick prescription. The result is pretty much all the neutron stars will get kicked out. Like, you'll only get max 1 or 2 neutron stars retained. So if we see this correlation, then we know that it's not due to neutron stars. But like I said, it's just a correlation. We're not saying that the structural concentration index is related to the black hole binary core mass fraction, but it's a decent enough correlation that we might be able to use it.
We do see some of the X-ray sources, which are accreting neutron stars that sit in globular clusters. So if you kick all out but 2, this probably would make it very unlikely that you have these sources in globulars.
For neutron stars, yes, but see, that's one of the reasons why I haven't really investigated neutron stars, is because most of them are getting kicked out from the natal kicks.
Not observation.
Well, yeah, this is, I went down that rabbit hole and I decided that it wasn't, it annoyed me, and I'll come, yeah, basically based on the observations, we know that pulsars exist in globular clusters, but also based, yeah, but we don't know why. Yeah, but that's outside of my area of expertise.
Okay, thank you. Any more questions? A much more basic question. So you spent a bit of time talking about how fast your code was, about how fast NBODY 6 was and how efficient it was. What's the loss in, how much slower is it with your additions versus the base code?
That's a good question. So on a basic level, my additions don't really slow it down at all, because so for the things like the remnant formation and stellar winds, because it was already doing those, all I'm doing is essentially slightly altering those calculations, but those calculations don't take any slower, and it's still doing the same number of calculations, so that doesn't slow it down. For the post-merger properties like the mass loss and recoil, because we're only getting a few mergers, like max 10 mergers per simulation, it's only happening 10 times over the entire simulation, they don't really slow it down either. The thing that does kind of slow it down is, because I said that the net zeroth order result of my stellar evolution updates is that we get more black holes, and those black holes are heavier. That can slow it down a bit because if you have more heavy things in the core, then essentially you're going to have need to do more. Like the time steps are going to be smaller, so you're going to need to do more force calculations. I haven't quantified what the difference is yet. It doesn't seem to be appreciable. The one thing it does do is it tends to break the simulations a bit more. So these aren't just set and forget simulations. You have to babysit them quite a lot. They tend to run into errors, like if it has a time step that's too small or energy is not conserved or things like that. My updates, as a result of having more heavy black holes, tend to break it a bit more. I don't know if there's an easy solution to that, but right now I'm just kind of dealing with it. It's just an unfortunate consequence. But yeah, in general, they don't really slow it down much.
Maybe I missed it, but how does an increased stellar winds or any stellar winds increase your black hole?
So it's not increased stellar winds, it's just an altered prescription for stellar winds. And yeah, well, so in this case, it's decreased. But so the stellar winds, it's not just ones, because the stellar winds depend on a whole bunch of things, which I'm not an expert in and not going to go into in detail, but like it depends on what evolutionary stage the star is at, what's the metallicity, what's the mass and radius, things like that, and like how hot is it? There's a whole bunch of things that I'm not in the know about really. But yeah, it's not increased stellar winds, it's just altered stellar winds. That one of the things it results in is slightly heavier black holes.
Okay.
Okay. So in many of these globular clusters, we also see two different populations of stars that have different abundances.
Yep.
And so it has been this model by, I think, Pavel Denisenkov was this first, and then maybe Corinne Chavinel later, where they looked at some rapidly rotating 10 to 4 solar mass star that would produce some helium that enriched possibly the second generation. But of course, it's a 10 to 4 solar mass star, and if it reaches the end, it may make an intermediate mass black hole of 10 to 4 solar masses. So to my knowledge, we don't see these in current globular clusters. But could you put one of these in and see what happens with it?
Yeah. So you'd have to mess around a bit with the code, but I mean, at this point, I'm pretty good at that. So yeah, that is like, I don't see why it wouldn't be doable. The one hard part, I suppose, is actually doing the evolution of that, because you'd have to do the evolution of that star quite.
Just put the black hole in.
Put it like start with an intermediate bus. Oh, we have done some simulations like that where you start with where we call it a primordial intermediate mass black hole, and I would refer you to work of my colleague Ruggero De Vita from a few years ago. He looked at how the presence of an intermediate mass black hole alters certain observational parameters.
Yeah, but to put it in the dynamic simulation, will it stay in the black hole, or can the spin thing eventually accelerate it and kick it out as well?
It could get ejected. In the simulations he did, he didn't have things like black hole spin or recoil.
Yeah, you can now do it.
Yes, I can. Yeah, so I haven't done it yet, but that is something I do want to do. But that would be kind of like a separate project. My first order guess is that it would get ejected quite often, but also that it would dominate the core because it's by far the most massive thing there. So I suspect that any merger that happens would be with it. Like you wouldn't have other binaries merging because they would just get exchanged with the intermediate mass black hole. But I suppose it depends. You'd have to check how does that change with different masses for the intermediate mass black hole, because I imagine it would quite heavily depend on what mass you're picking for it. But yeah, that's certainly an idea to try. It sounds like an interesting project.
Thank you. Well, it is 1 p.m., but Rosemary seems to have a question, but I'm waiting for the type. So let's just, yes. Rosemary, can you speak? Maybe we'll be able to hear you, hopefully. No, we still can't hear you. Sorry, maybe you can unmute your computer or something.
Yeah, press the join audio,
Sure.
green at the bottom left.
Yeah, just do the join.
Try again.
Yeah, now it's good.
Oh, okay.
Okay.
Well, thanks for acknowledging my dear old friend and colleague, Svera Arseth, who wrote all the codes up to NBODY 7. And actually, NBODY 6 has been developed a lot more by Rainer Spertzum. I don't know if you're in contact with him. But my question was going to be about the black hole spins. It's possible to evolve. I mean, they should evolve, right, through emission of gravitational radiation, both angular momentum and energy. And there are equations, you know, that you can put in with the two-body interactions to get this. You sort of alluded to that it was important to get the spin right.
Yeah.
And it affected the ejection rate and so on.
So, yeah, that's a good point. I currently, as I said, that when I assign the spin magnitude at birth and then I just leave it be. It is true that they can be spun up or spun down through things like gravitational wave emission and also...
Well, it's a dissipative process, so they will tend to evolve towards some kind of relaxed state, some kind of equilibrium state. I think it's probably quite important. It is important.
Yeah.
Final outcome, right? And you can do it. I mean, the equations that exist are these Kidder, but other people have, yeah.
Yeah, it's definitely something that would be important to consider. Like currently, I haven't included anything like that, but that's definitely a good idea for something I should include for essentially a next update. That's a good idea. Thank you for the suggestion.
Well, you could talk to Bernard Muller and Philip Podziolowski is visiting us at the moment, and they are, know a lot about peaks of neutron stars and black holes. So, you might get a better recipe.
Yeah.
And be able to say something about all the low mass X-ray binaries hanging around and pulsars hanging around in globular clusters. That's the answer in the back of the book, right? At least for those for neutron stars.
Yeah.
Well, and black hole binaries, X-ray binary. So, yeah, you want to try and reproduce that, huh?
Yeah, ideally. Yeah. Well, thanks for the...
Anyway, it's good to see this beautiful code being alive and well, revived, thanks to the gravitational wave interest.
Yeah. Happy to carry the torch forward.
Right, so I think it's already after 1 p.m, so let's thank Oliver again.